So welcome. Let's just to finish this chapter off. So we have this last little bit, which is energy stored in a charged capacitor. So let's talk about that process for a bit. And I want to emphasize that the got to find my pen. I want to emphasize that we have a capacitor and we are charging it up. So we have, and then we have 4, and then later on we have 5, and so on. So there's a process of charging. And that's what I'm showing here. I'm showing the process of charging. The charge is getting more and more as time passes. Now, I'm not plotting it against time. I'm plotting it against the voltage. Which voltage are we talking about? This is where I've got to be clear. I'm not talking about the battery voltage. The battery voltage is the battery voltage. You close the switch, and that voltage is applied. What we've got to be very clear about here is this idea that although this might be, say, 10 volts, as soon as I close the switch, there's 10 volts between the top of the plate of the capacitor and the very bottom of the resistor. That's where my 10 volts is applied. But it's not all across the capacitor, it's not all across the resistor, and it doesn't stay wherever it is. There's a change in time. And so what happens is, initially, there's no charge on the capacitor. So there's no potential difference across it. So the charge causes the potential difference on the capacitor, and you can think of it as the potential difference is linked to the charge on the capacitor. Fellas, please. So the charge causes the potential difference on the capacitor, and you can think of it as the potential difference on the capacitor is there because of the charges. So I can plot a graph of the potential difference. This is my potential difference across the capacitor. And as time passes, my charge increases, and so my potential difference increases. Now let's think about units. Voltage. Voltage was joule per coulomb. So this is in joules per coulomb. And what is charge measured in? What's charge measured in? Coulombs. So if I take joules per coulomb and I divide it by coulombs, so I get the slope, I'll get joules per coulomb squared. I have no idea what that means. It means something. I have no idea what it means. But if I take joules per coulomb and multiply it by coulombs, I get joules. And joules is energy. So the energy is the area under this graph. That's the energy. So what I can say is consider charging up a capacitor as the charge increases, the potential difference between the plates increases. Consider an instant when the charge on the capacitor is Q. The associated potential difference, well, delta V equals that charge over that capacitance, where this is the PD across the capacitor. I can say, well, work is equal to my joules per coulomb multiplied by my coulombs, delta V times little bit of charge dq, and this equals my charge over my coulomb dq, my delta V. I'm doing math here. Delta V, so that guy comes from there. So that's that. And then I can say, well, okay, the total work done is the integral of this. So I say, so on this graph, I can say it's my delta V times my delta Q. That's my little bit of energy I'm adding at that instant. And then I can integrate that. So I say it's the integral of this Q over C delta V. C is constant, it comes outside. The integral of Q dq, oh, I can do that. It's going to be Q squared over 2. So that gets me a half Q squared over 2, and Q is big Q for this. So that's the calculus way of doing it. There's the geometry way of doing it, and say, well, look, my delta U is equal to Well, what do we say? It was delta V times my total charge, which is Q. But it's a triangle, so it will be a half. A half the base times the height. So either way, I get an equation. I get one here, which is in terms of Q squared and C. I get the other one here in terms of delta V and Q. You've got to have a way in. Eventually, if you do enough of these, you'll know all three forms of this. But let me show you the way I do it. I really know well from the graph. I know delta U is equal to 1/2 delta V times Q. I know that really well. So that's one of my equations. And I also know really well that C is equal to Q over delta V. So I can say, well, delta V equals Q over C. Agreed? So substitute for delta V here. And this gets me a half Q over C times Q, which equals 1/2 Q squared over C, which is that equation that we had there. Yeah? So I got that. And if I want, I can say, well, okay, rather than substituting in for delta V, why don't we say Q is equal to C delta V? So now I come down here and I go, well, in that case then, rather than Q, I get C delta V. I get a half delta V times C delta V, which equals 1/2 C delta V squared. So there's one equation, there's two equations, and there's three equations. And I don't remember all three, because I don't do enough of these at any one time. But maybe if I did all the homeworks, by the end of the homeworks I'd have them, I don't know. But anyway, but those are the three alternatives you got to know. Okay? So if I look at this, what this kind of, well, anyway, so there it is, yeah. I'm trying to, so let's do a couple. How much energy is stored in a 6 farad capacitor? So here's my capacitor, little terminal at each end. C equals 6 farads. And Q at the moment equals 5 coulombs of charge. How much energy is stored? So delta U is equal to 1/2 Q delta V. That's what I remember. I want to know my delta U. Let's have a look. I want to get rid of that delta V. I know that my delta V, my capacitance, is equal to Q over delta V. So I know my delta V is equal to Q over C. So in here, I'm going to say this equals 1/2 Q times Q over C, which equals 1/2 Q squared over C, which equals 1/2 5 squared over 6, which equals 25 over 12, which equals 2.1. Close enough. 2.1 joules. Yep, 2.1 joules. That's a big capacitor. 6 farads. That's a big capacitor. And 5 coulombs, that's a lot of charge. And we got a whacking 2.1 joules out of it. Yeah, it's not the best way to store energy. How much energy is stored in a 9 farad capacitor? So here's my capacitor. C equals 9 farads. It's fully charged by a 9-volt battery. I'm going to change that. 9 and 9 is just like, you know, professionally negligent. So delta V equals 6 volts. And I want to find my delta U. So I go, well, delta U is equal to what I remember is 1/2 Q delta V. And let's have a look. Oh, man, I don't want that C in there. Oh, so this equals 1/2 Q. Let's have a look. I don't want that. Let's have a look. I don't want that Q in there. So I rearrange this again, and Q is equal to V delta V times C, So this is going to be, I don't want that Q. I'm sorry, I'm getting confused about what I want and what I don't want. I don't want that Q in there, so I'm going to go delta V times C times delta V, which equals 1/2 C delta V squared. So delta U is equal to 1/2 times 9 times 6 squared, which equals 18 times 9, which is 2 times 9 times 9 is 81, which is 2 times 81 is going to be 162, I think. Am I right on that? 162 joules. They're not bad, are they? It's just... Last little thing. Okay, how is the energy stored? And the energy is stored in the electric field. So we say, well, V is equal to minus ED, and we say C for a capacitor equals epsilon naught A over D. I'm forgetting about the K. I'm going to say it's an air-filled system. So I say, well, my energy is equal to 1/2 C delta V squared. I got that from the previous page, which is 1/2 epsilon naught A over D. There's my C. And there's my delta V. I'm going to square it. So I get 1/2 epsilon naught A D E squared. And I say, well, so then I have that expression. And by the way, A times D is going to equal the volume of the little bit inside. That area times that is the volume. So from a physicsy point of view, my energy storage depends upon the area. That makes sense, bigger capacitor. But more than that, it depends upon the area, the volume. So if I open the gap, as long as I can keep the same amount of charge on there and all that, I get a bigger energy. And also, it depends upon the electric field squared. If I can double the electric field, I get 4 times the energy. If I double the volume, I get twice. So then that raises an issue of, well, how much energy per unit volume can I get? And it's just basically 1/2 epsilon naught times E squared times electric field squared. This expression is valid for many different capacitor configurations, parallel plate being the primary one. The energy density of an electric field is proportional to the square of the magnitude of the electric field at that point. Frankly, I don't expect you to know those equations. It's like I've got to make some choices here. When there's no equation sheet, I've got to make some choices. But I'm not above giving you that equation and then saying, hey, plot me a graph of the potential energy versus the electric field for a capacitor. And you've got to look at that expression, which I'll give you, but you've got to be able to do the skill on it. I don't do it very often, but I'm not above doing it, because what I've found is that when I say there's no need to know that equation, people seem to think that means even recognize that it exists. And I'm just saying you don't have to commit that to memory, So, cool. So let's